a block of mass m of 3.3 kilograms hanging from a massless cord that is wrapped around a pulley, which is not massless. It is 6 kilograms as shown in the figure. Figure shall be drawn. The cord does not slip, which means that the x equals r theta, v equals r omega, a equals r alpha. That's supposed to be an a. And that just tells us the relationship between the linear and angular motion. As the block falls, find the magnitude of the tension in the cord, and then it gives us the moment of inertia of a pulley, which is that of a disc. Okay, so we're going to have a pulley. That's a reasonably good circle. We're going to have a string wrapped around it, and it is going to go down. It's going to be attached to a block. So this block has mass m, and I'm going to do a free body diagram here. So we're going to have force gravity of the block going down, and then we're going to have tension going up. Then on the pulley, we're going to have tension going down, and we're going to have a radius here of r. Yep, I think we're good at that. So the idea here is we're going to draw or write out the sum of all forces for each of these free body diagrams. So we're going to start by looking at the block down here. So I'm going to say the sum of all forces on, I'll call it the block B, is going to equal, I'm going to call down positive. It doesn't really matter as long as you stay consistent. Force gravity minus tension, and that's going to equal mass times acceleration. In this case, it's going to be mass of the block times acceleration A. And that's terrible. I'm going to call it A, not A specific to the block, because since it's attached to the string, everything's rotating at the same rate. So now we're going to do, we really don't want to talk about forces in terms of the pulley. We're going to talk about torques. So I'm going to say the sum of all torques equals moment of inertia times alpha. And this is the exact same idea as sum of all forces equals mass times acceleration, except instead of mass, we're going to use moment of inertia, and instead of acceleration, we're going to use alpha, angular acceleration. So we also know that torque equals r cross F, and that's the perpendicular moment arm times the force, where in this case, since r and tension are perpendicular, r cross F is just going to be rf, and in this case, F is going to be tension, so r times tension. So the sum of all torques, there's only one torque, and that's the tension pulling down, and that's going to equal r times tension. So torque, r cross F, in this case r tension, and there's no sine or anything like that because they're perpendicular. So you could say the sine of 90 degrees, which is 1. R times tension is going to equal moment of inertia times alpha. Moment of inertia we know of a disk, which is what this pulley is 1/2 mr squared. So I'm going to do 1/2. I'm going to call this the mass of the pulley times r squared times alpha. Now I'm going to rewrite alpha real quick. We said A equals r alpha. We got that Q by the phrase does not slip. Therefore, alpha, if we rearrange this, is going to be acceleration over r. And I want to write this in terms of acceleration because, well, we could use angular acceleration either. I just feel more comfortable with linear, so I'm going to go with that. So we're going to get write in alpha, which is a over r. All right, so we have a bit of a mess here, but that's okay because we can clean this up. This r cancels with that r cancels with that r, and so we get tension equals 1/2 mass of the pulley times acceleration. So now I'm going to look at these two equations right here. I'm going to look at this equation and this equation. I know that mass gravity is going to be mass of the block times gravity. And so with an equation, you can always, as long as you do the same thing, the equal thing to both sides, then you can do it. I know that sounded terrible. So the idea here is I'm going to add tension to the left side, and then this 1/2 mp mass of the pulley times acceleration is the same as tension, so I can add that to the other side. So I'm basically going to add both of these equations together. You'll see, it'll be great. So I'm going to get force gravity on the pulley, which is going to be mass of the block times gravity, minus tension, so that's the left side right there. Then we're going to add the left side of this one, which is plus tension, which equals mass of the block times acceleration plus 1/2 mass of the pulley times acceleration. So now, at this point, we can see this right here. This cancels out. Negative tension plus positive tension, negative T plus T, that equals 0. Doing some algebra, we get mass block gravity equals acceleration times mass of the block plus 1/2 times mass of the pulley. Yep, that works. And then we can say that acceleration equals, I'm going to write this as gravity, mass of the block all over mass of the block plus 1/2 mass of the pulley. Plugging that into a calculator, we know that gravity, I'm going to say gravity is 9.8. So I'm going to do 9.8. I'll say 9.81. It doesn't really matter. They're both close. Mass of the block is 3.3. And then we're going to divide by 3.3 plus 6 divided by 2. Because 6 is the mass of the pulley. Quite the hefty pulley. And we get an acceleration of 5.138 meters per second squared. So now we want to find, what are we trying to find? Find the magnitude of the tension in the cord. So we don't care about the acceleration per se, we care about the tension. But we have two equations up here with tension, so we can go back up and find them. And the one I'm going to use is the second one right here, just because it's easiest. So I'm going to take this equation, which we already found, move it down here, and I'm going to say that the tension, therefore, is 1/2 mass of the pulley, which I think was 6. 6, yep. 1/2 times 6 times acceleration, which is 5.138. So basically, we're going to take our previous answer of 5.138, multiply it by 3, which is 1/2 of 6. We get an answer of 15.4 newtons. And so the tension in this wire, string, did we say cord, is going to be 15.4 newtons. The way we did it was we drew a picture, did a couple free body diagrams, wrote out an equation for those free body diagrams using force equals ma, and torque equals moment of inertia times angular acceleration. Same equation, just different ways of looking at it. Did some algebra, found answer. So not too bad at all. Hope this helped if you had trouble with these kind of problems. And see you on the next one. Bye.